Okay, the next step in our project is to look into this idea of channel equalization. So before we get started on that, I wanted to give you a real simple example of what it means to have equalization. I remember when I was an undergraduate student, equalization always seemed like a mysterious term to me. I didn't understand exactly what it meant. So let's do a simple example that hopefully firms this up a little bit for you. All right, so in this simple example, what we're going to do is we're going to look at a signal that is just simply an echo. All right, so if this were an audio signal, we'll run this in MATLAB real quickly too. If this was an audio signal x of n, and I had x of n attenuated a little bit, only by 0.8, multiply by 0.8, and then delayed by nd, where nd is another integer. Okay, this would be a simple echo, and later on in this chapter we'll talk about these delays like this would be a way to model multipath. Okay, but let's not get ahead of ourselves. Here's this echo signal. All right, so one way you could think of this is that you have x of n, and you have a filter h, all right, capital H. I know not everybody's had DSP, but this would be in the discrete domain, so this would be h of z, and out comes y of n. Okay, well, an equalizer would be, what would you do to undo the effect of h? Okay, so think of the echo process as the channel, all right, and we send the signal through the channel, we get the output, and we'd really like to recover the original signal, possibly delayed. Okay, delay is okay, but we want to have it sound the same. Okay, so that's the goal here. We want to come up with this equalizer. All right, so again, I realize you all haven't had DSP, but if you have had DSP, this is a simple calculation to find the equalizer, and if you haven't, I'm still going to go over it, because when you get to DSP, and that's a required course in our curriculum, when you get to it, you'll hopefully remember, this is just a real simple case of making an equalizer. Okay, so the way we would do this is I have y of n, which is x of n minus 0.8, x of n minus nd. So the simple calculation goes like this. To find h of z, I take the z transform, and this is very similar to Laplace, so everybody's had Laplace, so you can take the same ideas. Okay, so that you take the z transform, x of z transform of x is x of z, z transform of y is y of z, and then there's some math that you may not have had if you haven't had DSP. The transform of a delayed signal is z to the minus delay term, z to the minus nd, x of z. All right. So from that we can solve for h of z is y of z over x of z, and we get that it's 1 minus 0.8 z to the minus nd. Okay, so awesome. That's the this is the transfer function h of z. All right, so if I wanted the equalizer, then that would just be 1 over h of z in this case. All right, and so that's pretty easy. 1 over 1 minus 0.8 z to the minus nd. Okay, so that's the equalizer transfer function. And again, if you haven't had DSP, this might not mean much to you, but the point of this is it's possible to undo the effect of the channel. All right, so take that as the moral to the story here. All right, so with the echo signal, I can generate that by using the A's and B's we've talked about. It's been a while since we talked about it, but we can use the A's and the B's. And so the original h of z would have 1 and then a bunch of zeros, and then I guess that would be in d minus 1. And then it would have a 0.8. Well, minus 0.8 because I subtracted that echo. All right. And the a vector would be 1. So this is what you'd use to implement h of z in MATLAB. Okay. And so to implement HEQ, you notice they're just flipped over, and that just flips the role of A and B. Okay, so with the equalizer filter, the B is going to be 1, and the A is going to be the old value of B. Okay, and so when you implement these filters back to back, it will undo that multipath effect or that echo effect that's shown in this example. Okay, so at this point I'm going to turn to MATLAB and quickly implement this on a speech signal.
The first thing I'm going to do here is load a speech signal. So audio, read, speech. And I happen to know that the sampling rate of that file was 8,000 samples per second. And so we can play that, and we know what the original sounds like.
Notching and peaking filters are referred to generically as cone filters. Notching cone filters are typically used to cancel periodic interference such as the power.
Okay, so there's the speech signal. Now, to implement this echo effect, I put in 1, zeros, 1 comma. I'm going to make ND a pretty big number so it will be obvious to hear the echo. And then we'd have minus 0.8 as our last term in this B vector. And then A is going to be equal to 1. All right, so we have this, I'll call it YD for a delayed version, or YE for echo. All right. YE is going to be filter, and then we put in B first, and then A, and then the signal. Okay, so we can play that.
Notching and peaking filters are referred to generically as cone filters. Notching cone filters are typically used to cancel periodic interference such as the power.
Okay, so it's really obvious that that's an echo. All right, so remember, the signal at this point with the echo is called YE. So let's filter YE to get rid of the echo. And we use B's and A's, but it turns out we just flop the roles. Okay, so A2 is going to be equal to B. I'm sorry, A1. We have an A and a B, now we have an A1 and a B1. Okay, so we just interchange the roles, and I'm going to come up with Y filtered, and that's going to be B1, A1, and YE. All right, sound YF.
Notching and peaking filters are referred to generically as cone filters. Notching cone filters are typically used to cancel periodic interference such as the power.
So there you go. It sounds like the original. The echo was removed, and effectively we did a really simple version of channel equalization with this example.